Introduction to Linear Approximation. In general, in mathematics, the curvier something is, the harder it is to work with, and the straighter something is, the easier it is to work with. Such as a line, right, is very straight, and we can deal with lines all day, and then we have all kinds of crazy curves that we know from trigonometry and inverse trig and all that become harder and harder to deal with the, curvier that they get. So the idea with linear approximation is that we'll use lines to approximate a curvy function because lines are easier to work with. Now, how can this work? Let's draw a little diagram and look deeper into this a little bit. Okay, so here's a curvy function. We'll call this f of x. And we essentially use the tangent line at a point. We'll call this point A. This will go down. This will be point A, x equals A. And we'll essentially examine the tangent line at this point as an approximation for the function around the point x equals a. So notice, as long as we stick around the point x equals a, this is a pretty good approximation. Look, the red and the black don't deviate much, but if we come out here far from a, this is a bad approximation. Look how far off they are. We have f of x way up here, but the linear approximation is way down here. So the idea is you select a point that you're interested in, we'll call it A, and then you do the linear approximation at that point A. But that linear approximation is simply the equation of the tangent line, and it's the same equation of the tangent line that we've been talking about this whole time. So let's dig a little bit deeper into the equation of this linear approximation, and then we'll have something we can work with. Recall that for any point x1, y1, as long as we have the slope of the line, we can get an equation for the line. We call this point slope form, y minus y1 equals m times the quantity x minus x1. Let's see how we can use this to come up with our equation for a linear approximation. First off, our known quantities here, instead of being x1, y1, our x value that we know is a, and the y value that corresponds with that value a is simply f of a. Right? We plug it into the function, out comes the y value. So there's our x and our y, our x1, y1, so to speak. Okay, our slope, of course, well, this is the equation of a tangent line, so our slope will come from f prime of a. Right, the derivative of the function evaluated at the point A will give us the slope of this linear approximation line here. Thus, we have y minus, we decided y1 was f of a, equals m, we decided that was f prime of a, times x minus, we decided x1 was a. Next, we essentially solve this for y, but instead of y, we're going to write this as the linear approximation of x, so we'll call this L of x. L of x equals, we add the f of a to both sides, f of a, and then plus, we still have left over here, f prime of a times the quantity x minus a. This here is our linear approximation at the point x equals a. It will be a really good approximation when x is close to a, and the further off from a we get, the worse of an approximation this will be. So these are really good for local approximations, but they start to give a lot of error once you get further and further away from the point x equals a. Let's try an example. Find the linear approximation of f of x equals e to the 3x minus 6 at the point a equals 2. Okay, we can do that. So we have our function here, f of x, and we're also given an a value, a equals 2. Okay, so now we look at our equation for L of x and fill in our pieces as we go. We need f of a and f prime of a, and in this case, a equals 2. So let's evaluate f of 2. F of 2 is, okay, so I'm plugging in 2 to the function, that's e to the 6 minus 6. Well, e to the 0 is happily 1. That's a big relief. That's really nice to have. Always nice to get rid of the e values when you can. Alright, next we'll move on to the derivative. Let's first just compute the general derivative, f prime of x, and then we'll plug in 2 to see what it is at x equals 2, or a equals 2 in this case. Okay, derivative of e to the 3x minus 6 is e to the 3x minus 6 times derivative of this top part here, so that's times 3. So it's essentially 3 times e to the 3x minus 6. What we really need, though, is f prime of a, which is 2 in this case. So both of these were, this is f of a was f of 2, and f prime of a was f prime of 2. Okay, plugging in 2 here, we have 3 e to the, again, 6 minus 6. So that's 3 e to the 0, so that's 3 times 1, which is 3. Okay, and that should give us everything we need. Let's go ahead and plug everything in to get our L of x, our function here. We decided f of a was 1, plus f prime of a was 3 times the quantity x minus 2. And now we clean it up and make it look nice. Usually I put it in y equals mx plus b mode because it is a line after all. So let's see here. 1 plus 3x minus 6 is finally 3x minus 5. Look how simple the line is for this linear approximation compared to the function itself, right? A lot easier to work with. So this line will be valid, at least somewhat valid, as long as we stick close around a equals 2, and it will become less and less valid as we move away from a equals 2. Let's look at this in Desmos just to see what this means. So here we go. I have the blue function, which is e to the 3x minus 6, and the green function, which is our linear approximation. Note that right at that point, 2, 1, they're exactly together, and then right around that point, they're pretty much on top of each other. And then as we get further and further off from the function here, the approximation and the function deviate more and more, right? So this is really a very nice approximation right around the 0.21, but then you can see as we go off in the function, look here, if we tried to look at it at 0, they're completely different, completely far off. So it's good right around that point.